Okay. Okay. Thank you. Thank you, Purushottam. Thank you, the organizers. We're happy, well, to be at least virtually, to be here in, well, in Madras, in one of my favorite places in the world. Well, so good morning, good afternoon, good evening, good night to everybody around here. So I will be speaking on a recent work by Veselin Dimitrov, who proved the old conjecture of Schinzel Zassenhaus, which was open since 1965. So just to compare, I was born just a year before 1964. So basically, all my life, this conjecture was here, and I survived it. Now I'm still here, and it is no longer a conjecture. So I will now. I decided against using slides because, well, there are two main reasons. First, that slides go too quickly, and second, that, well, I'm still did not learn well how to write. If I have a question, I have to answer and I have to write something, and when it's a PDF file, I'm not sure that I'm able to do it. And there is also a secret reason that I will not tell to you, and so I'm not telling you that I was just lazy to make slides. So I will write. I will write just on the screen using some fancy application. Well, you will not see my face because I have to put my screen down. And well, let me share it. Okay. So it is Schinzel. Oh. Conjecture. Well, just some organization point. I will right now. Then I will, at the end of the lecture, I will transform all these notes into PDF, and I will put it on some file depository. I think most of you already got a link to this depository. Those who did not get, don't hesitate to write me an email, and I will send you a link. Okay, so let me start. So throughout this course, I presume that Q bar is an algebraic closure of Q in C. So all algebraic numbers are just complex numbers, period. Now, usually in this course, alpha will be an algebraic integer of degree D. Of degree D. So I hope that my way of writing letter alpha and my way of writing letter D are not the same, so you can distinguish. And well, I denote by alpha 1, that will be just presumed to be alpha itself, then alpha 2, etc., alpha D, its conjugates over Q. And then we have two quantities that somehow measure the complexity of our alpha. One quantity is called the house function, the house of alpha, is just the maximum of absolute values. So they are all complex numbers, so we can just take the maximum of their absolute values. The other quantity, it is called Mahler's measure, perhaps more famous. And this is the following guy. It is the product of absolute values of those who have absolute values bigger than 1. So some of them, so if we draw a unit circle, so let's assume that this is a unit circle on the complex plane, so 0, 1, we'll assume that this is a circle. Some of them will be outside, and some will be inside. So we only count those who are outside in this product, only their absolute values, not those who are inside. These are counted, these are not counted. Okay. And well, the starting point, there are two very, very classical theorems of Chronic. Actually, I will speak in this course mainly about very classical things. I believe that the work of Dimitrov can be explained to a mathematician that was active like 100 years ago. Well, not all results were already ready by that time, but even those that were not available at that time could now be explained to people who were working at that time. So it's really one of the amazing features of Dimitrov's work that he uses only very, very, very classical things. So we have theorems of Chronic. Okay. First theorem. Well, clearly both, or perhaps I had to say that both House and Mahler's measure are greater or equal 1, and well, they satisfy the following like trivial inequalities. So it's trivial, so all clear. And theorem of Kronecker, it first tells when it can be 1. Well, perhaps I had to say that non-zero alpha will be always assumed non-zero algebraic integer. Otherwise, this already is not true. So theorems of Kronecker. First, well, the house is 1 if and only if, well, let me put it like this. The Mahler measure is 1 if and only if the house is 1, and if and only if alpha is a root of unity. And second, well, if it is not 1, then it's very important observation of, probably again, of Kronecker, that if it is not 1, then it cannot be too close to 1. So it is separated from 1 by some quantity which depends only on the degree. So if alpha not a root of unity, then, well, it will be more convenient for me to write not that alpha is separated from 1, but that the log alpha is separated from 0. by some quantity depending only on the degree, some positive number. Well, these theorems are very classical, and I'm sure that, well, most of you know their proofs and can tell it being way woke up at night, but still I would just since I'm starting the course, I want to start from something simple, so I would prefer to prove them. And proof requires another elementary and important statement, which is called Norcote Lemma. And this is the following. If C is some positive number, then there exist at most finitely many algebraic integers such that both house and degree are bounded by C, integers alpha. Well, proof of the lemma is well known and very simple. We fix some alpha like this, like satisfies star. Then, well, denote f of x so to be, well, wait a moment, proof, well, sorry. Well, proof of the lemma, well, it's enough to prove the following statement. Well, we may fix the degrees, and there are only finitely many possible degrees. We may assume that the degree of alpha is fixed. Enough to prove finiteness of alpha with the property so let me note this call star such that degree is equal to D and the house is bounded by C. So fixed degree and bounded house. And well, take alpha like this. And consider its minimal polynomial. Or it will be xd to ad minus 1 xd minus 1 plus etc. plus a0. It's minimal polynomial. Then for the coefficients, we have clear estimate, well, a d minus k. What is this? It's the case symmetric function up to the sign in the conjugates. So we have this many terms, and each term is bounded by the house raised to the power k. So it is actually bounded to 2 to the d, c to the d. And this means, since the coefficients are integer, this means that we have only finitely many possibilities So we bound the coefficients and they are integers, so there are finitely many possibilities f for polynomial f, and hence there are finitely many possible alpha. And this is the end of the proof of this Norcote lemma. Now we can prove the theorems of Chronic. Maybe let me start a new slide. Chroniker. So, first statement, remind what it was. Equivalent alpha root of unity. Alpha non-zero algebraic integer. So this is obvious. And here when it is root of unity, then clearly house is 1. So this direction here is also obvious. So we only have to prove the following, that if house is 1, then alpha is root of unity. So what we do the following. We take the numbers 1, alpha, alpha squared, all powers of alpha. And all these numbers, they have house equal to 1 and degree bounded by the degree of alpha. So they have bounded house and they have bounded degree. Hence, this set is finite by Norcote Lemma. And so, for some m smaller than n, we have alpha m is equal to alpha n. And since alpha is non-zero, this implies that alpha n minus m equal to 1. So alpha root of unity. This is the first. And the second statement, we want to show that if alpha is not, alpha is not a root of unity, then the house is separated from 1, or log of a house separated from 0 by some quantity depending only on the degree. And here the proof is again very easy. We consider the set of all algebraic numbers, beta, integers, such that the house is strictly between here 1 and 2, and the degree is 2 here, and the degree bounded by D. It's a non-empty set, and it is finite by Norcote. Call this set S. Okay. And since it is finite, well, it's finite by Norcote, it's non-empty because, for instance, 2 is there. And since this set is finite, it has an element with smallest house. So we denote by C of D the smallest house of elements of this set. And then we're clearly done. Because, well, if our alpha does not belong to this set, then it's house at least 2. If it belongs, then it's house at least this C of D. And it is a positive number.
So maybe you want to take the log of it.
Oh, yeah.
Oh.
Okay, thank you. Thank you. And now, the basic question, what is this C of D? This is the main question that we will study. And, well, we can pose the same question for house and for Mahler measure, because, well, it implies, Kroneker's theorem also implies that that Mahler measure is also bounded by the same C of D, or log of Mahler measure. And, well, one can ask this question both for house and for Mahler measure. And, well, probably historically, the first one who was interested in this question in the context exactly of Mahler measure was Lemma. On some article where he studied some primarity tests or whatever, well, I must admit that I do not completely understand the topic of what Lemmer wants to do in this article. But in the context of this article, which was written as early as 1933, sorry.
Yuri, there is a question from Akash.
Yes.
Sir, so just a minor confirmation. So here you're asking the question whether there exists a C of D more than one, right? Unlike
Sorry?
before. So here we're asking whether there exists a constant C of D which is strictly more than one, right? Unlike before where it was just strictly positive.
No. No, why? It is
okay,
log.
no, we're taking the log. Okay.
Yes, it is log. It is still log.
Okay.
Yes.
Okay.
And what Lemmer, he did some extensive calculations, and he was very amazed to discover, well, which calculations in that year he could do. I don't know. Probably he used some pre-images of computers, well, what existed by that time, but, well, he did quite a lot of calculations, and he was quite amused to discover that in all examples he found, Mahler's measure, is separated from one by something, just some absolute constant. So Mahler's measure was bigger than a certain number. I will now say what it is, which is about 1. Now I put 1 because I put Mahler measure, not the log of Mahler measure, okay? 7, 6 to 8, etc. Where what is eta? Eta root of the following wonderful polynomial, x10 plus x9 minus x7 minus x6 minus x5 minus x4 minus x cubed plus x plus 1. It's a reducible polynomial, and its root is an algebraic integer, and its Mahler's measure is this. And he discovered that he does not know any, well, he could not find any example of an algebraic integer which has Mahler measure smaller than this. And he just asked a question. Is it true? So people now speak about Lemmer's conjecture. It was not a conjecture in his article, it was a question. He did not really make any conjectures. He just asked, is it true that for every positive epsilon, there exists an algebraic integer alpha such that the Mahler's measure is strictly between 1 and 1 plus epsilon. And well, he said that for epsilon smaller than just 0.76, 28, etc., he could not find a single example. But he did not know. Maybe he just was not, he did not know whether he was not looking far enough. Now, at this time, almost 100 to 90 years after, we still do not know a single example of an algebraic integer whose Mahler's measure is smaller than this. So now we can speak about Lemmer's conjecture, that the answer to this question is negative. Though people often call it Lemmer's conjecture, though I again say Lemmer himself did not state it as a conjecture. That Mahler measure is separated from 1 not just by some constant depending on d, but by some absolute constant. There exists an absolute constant c, such that if alpha is not a root of unity, then Mahler's measure of alpha, logarithm of Mahler's measure, is greater or equal c. Well, conjecturally, even more optimistic conjecture, that the c is exactly the logarithm of that number theta. So I think something like 1/6, I believe something like 0.62, etc. I forget already how much. Well, Lemmer's question was not really much noticed for like 30 years. And only in 65, Schinzel and Zassenhaus made the first attempt to prove something. And they proved some lower bound. They actually argued concerning the house. And in particular, they conjectured, or again, they asked a question, they more asked a question, but now people call it usually conjecture. Is it true that for the same alpha, log of the house is bigger, greater or equal than C over D, where C is again absolute constant? So it's clear. So let us call this L conjecture, and let us call this SZ conjecture. Well, clearly that Lemma conjecture is formally strong. It implies this conjecture. Let me also make some trivial remarks. Well, we cannot say anything better than this. Moreover, the constant C here cannot exceed, in both conjectures, cannot exceed log 2. Actually, one can say even more than log 2, but well, let's put it so we cannot just do it for some big C. Well, log 2 at most, simply because of the trivial example, this root of 2, for which, well, this. And second, also trivial observation is that if alpha is not a unit in Dirichlet sense, then, well, both hold trivially and SZ hold trivially with again with constant log 2, simply by taking the norm. So the D log alpha greater or equal than log of Mahler measure, and this is greater or equal than the log of absolute norm of alpha, and this one is at least log 2 because it's not a unit. So we may assume that alpha is a unit. We will not make much use of this assumption, but it will be useful to keep in mind that alpha is a unit. Well, now let us speak what is known. Well, there are really many results. Already Schinzel and Zassenhaus proved something in their article. I will return to this. Now let me mention only two really key results. First, in 1971, Chris Smith, at that time PhD student of Castles, proved the following, that Lemma's conjecture is true for non-reciprocal integers, algebraic integers. What is non-reciprocal? So we call alpha is reciprocal if alpha and alpha minus 1 are conjugate over Q. And in fact, he even obtained the best possible result. He proved that in this case, for non-reciprocal alpha, Mahler's measure is at least theta, where theta is a root. Well, it is. Oh, I made something wrong. Oop. Sorry. And it is kind of 1.32 something. And it is what? It is the real root of the polynomial. It's also known as the smallest PV number. Well, it is an absolutely marvelous article. I actually had a plan to prove, well, not maybe exactly the best possible result, but some weaker form. But I'm not sure, I will still need some time, like maybe 15-20 minutes to prove it. So let me postpone it. If by the end of my course some time is left, this will be my priority to prove the theorem of Smith. It's really, really very beautiful. Really marvelous article. So we can now consider only reciprocal numbers. Again, we will not make much use of this in our work, but one can keep this in mind. And second result about Lemma's conjecture is the following, is the, again, very famous work of Dobrovolsky. Again, very long ago, in the year 79. And he obtained, without assuming anything about algebraic number, he obtained the lower bound of the form, well, a bit strange, log d over log d. Well, let me put it d star cube, where d star is just, well, just to avoid some stupid things like negative log, so I put it maximum d and 3. And this is Vinogradov notation. So for those who are not familiar with Vinogradov notation, so A Vinogradov smaller than B is the same as A is big O of B. And big O, well, has some bad feature. It is not, you cannot just swap them. You cannot write O of B is A. But here it is perfectly swappable. We can write instead A like this. We can write can write this. So in certain cases, Vinogradov's notation is more convenient. And here simply means that we can put here some positive absolute constant. And when Dobrovolsky came with his work, I think, well, I remember there was some enthusiasm that very soon, Lemmer's conjecture would be proved, or at least Dobrovolsky's this strange estimate will be improved. Well, it did not happen. It still stands as the world record. Well, there was some work on the value of this implied constant, but this is all. The asymptotics is still like this. There were many generalizations to elliptic curves, to multidimensional cases, abelian varieties, whatever, but in the most basic case, just one algebraic integer, it is still this. Nothing better is known. So Lemmer's conjecture is still open. On the contrary, the slightly weaker Schinzel Zassenhaus conjecture is now a theorem. So Veselin Dimitrov in very end of the year 19, December, I think it was December 28, 2019, proved the following, that if alpha algebraic integer, not a root of unity, non-zero algebraic integer, not a root of unity, of degree d, not a root of unity, then its house is bounded by C over D, where he gave an explicit version of this constant, log 2 over 4. Constant is certainly not best possible. There are again some conjecture for what best possible constant is, but well, he already this result I find very, very impressive. Okay. Now I can give the plan of what follows. So first I will speak on what is called, well, some nice stuff like what's called Schoenemann's congruences. Which is a tool in both the work of the Dobrovolsky and Dimitrov. Second, I will briefly review Dobrovolsky's argument. We don't formally need it, but it is very clever and I think very instructive, so I will speak on it. Next, I will give a very, very brief introduction to the notion of transfinite diameter in complex analysis. Oh, my God. Next, I will speak on power series again, some result which is on the border, on the boundary between complex analysis and number theory, the beautiful theorem, classical theorem of Poya about power series with integral coefficients. Well, all this stuff is very old, really very old. And finally, when I have this, I will speak on Dimitrov's arguments, and it will not take much time. Basically, it follows easily from properties of transfinite diameter of certain sets and of the theorem of Poyer. And if time permits, I will also include the proof of theorem of Smith. So this is the plan. This is the plan of our article. Not article of this course. Okay. So it's exactly half of the time. So let me start now. This was kind of introductory part. Let me start now from already doing mathematics. So far there was no. So I will now speak on the first part, Schoenemann's congruences. Well, Theodor Schoenemann was a German mathematician of early or first half of 19th century. Well, he was a decent mathematician. I'm not sure whether there is E here. Probably there is. Oh, I'm not sure. Decent mathematician, but well, he was maybe lucky or maybe unlucky that he was working at the same time with giants like Riemann and Dirichlet and Kummer and Dedekind and all these people. And of course, kind of he was a bit forgotten because, well, there were too many much more important people in the history of mathematics or German mathematics at that time. Still, he did some important, interesting stuff. And well, to start, let me remind there is little Fermat. For every A in Z, and P will always stand for prime number unless I say otherwise. So this is little Fermat. And well, we can Euler is AP and congruent to A Pn minus 1 mod Pn. It's Euler. And Schoenemann's congruences are certain generalizations so let S be a finite set of algebraic integers with the following property: S is closed under Galois conjugation. Then the sum of pth powers of elements from S, well, since it is closed under Galois conjugation, it is a rational integer, is congruent to the sum of just elements of S. This is exactly Schoenemann's result. But we will need also a generalization of this result, more generally.
Yuri, is it mod P? Or?
Sorry?
The congruence is mod P.
Yes, mod P, yes, mod P. Yeah, sure. More generally, the sum of, well, congruent to the sum n minus 1, and here mod P to the n. Well, Schoenemann proved first. Second, well, on the second, it's kind of thing that, well, was discovered and rediscovered many times. I think, well, I don't really know. I thought until recently, until maybe today, that the first proof was in like 1921, or the second statement by Satan Jenichen. But today, Tom Ward showed me some references that probably even before it was known. Maybe even Gauss was aware of this congruence. So, well, I don't really know. This probably should be credited to Schoenemann. I don't know the first one. I don't know whom should I credit the second. So let me call them both Schoenemann's congruence. So, well, I will prove the first one, which is very easy. Well, it's really very easy because just one line. Well, it's really congruent to the sum of all of them. Raised to power p, well, simply properties of multinomial coefficients. And this is congruent, of course, to the sum. Since it is a rational integer, this sum, this is by little Fermat congruent to itself. And we're done. So this is little Fermat. Well, concerning 2, well, I do not want to prove it. Well, there are, as I say, many proofs. I personally like a proof that can be found in an article of Winberg. You can find it in the depository. So probably the first one, as I saw, was due to Satan Jenichen in 21. Then there were several modern proofs. Well, Chris Smith in Monthly gave some proof. Next, well, Winberg recently, well, published in a proof, and also Delin gave a very short proof using bit vectors. So, as I said, was discovered and rediscovered by many people. And well, today, Tom Ward showed me maybe 5 more references where this was proved. So these are not, the list is very incomplete. But none of these proofs is really a straightforward generalization of the case of the Fermat. So here Well, classical Euler is a straightforward generalization of classical Fermat, just if you use the group theoretic language. Here it is not. One should do, in any case, one should do something. Either just work more carefully with congruences as Weinberg does, and I really like how he does it, or employ some dynamical stuff, or employ some like some fancy stuff like Delin does. Well, actually, a nice interpretation in which things become really good is equivalent statement is the following. If A is a square matrix with integral entries, then the trace of, well, let me put it here, n is already used. Okay, let me put it here. Trace of A to P to the n is congruent to trace of A to P to n minus 1 mod Pn. Well, this statement is clearly equivalent to what I stated. And well, this has a proof using some dynamical ideas and so on. So there are really many proofs. I'm not going to give any of them, but you can consult, well, any of the 3 articles. They are available on the depository. Okay. Now let me show the way we're going to use it. So let f of x be some polynomial with integral coefficients of degree d. And let us write it as, well, like this. And we denote by Fn a same polynomial whose roots are nth powers of the roots of f. So it is just and then corollary 1. The polynomial f, this is also, of course, a polynomial with integral coefficients. F is congruent to fp mod p. Or more generally, f p to the n is congruent to fp n minus 1 mod p to the n. Well, how it is clear? Yeah, on the coefficients of level d minus 1, they're just sum of the roots up to the sign. We just use the previous statement with a set S consisting of the roots. For coefficients of level d minus 2, we use the same statement, but with S consisting of products of 2 roots. And so on. So, using for the sets S, we obtain congruences for the corresponding coefficients. So, corollary 2. Corollary 2. the resultant of f and fp is divisible by p to the d. Well, this is why it's clear, because what is resultant? It's just the product fp of alpha 1, fp of alpha d, and each of these is divisible by p, because fp is congruent to f and f of alpha 1 is 0. So this is divisible by p, and all of them. And so we obtain product of d terms divisible by p. And also the discriminant of the product of two polynomials f and fp is divisible by p to the power 2d. And again, this is very easy, because the discriminant of their product is what? Is equal to the discriminant of f, discriminant of fp, times the square of their resultant. And then we use the previous corollary. Okay. This is all about the congruences, and now I will show the first application of these congruences. Is Dobrovolsky's argument. It will be our section 2 of this course. This is a direct application of the Schoenemann's, or the simplest Schoenemann's congruence. So let us just to make some introduction what we are going to do. So as I said, the first non-trivial work was due to Schinzel and Zassenhaus, and they proved a rather weak estimate. They proved that Haus is bounded by something, well, I don't remember exactly, well, some exponential of the degree. Very weak result. Still, it is stronger than, well, if you just use the proof of the theorem of Chronic, you obtain even something weaker. But, well, this was already non-trivial, at least non-trivial. There were some improvements that are not worth mentioning. And the cardinal improvement was in the work of Blanksby and Montgomery in 71, same year when Chris Smith came with his wonderful argument. And they proved already something much more interesting. They proved that, first of all, they proved lower bound for Mahler's measure, not just for Haus. And it was not exponential, it was quite almost polynomial function. it's quite decent. Well, some constant is hidden here. And this implies, of course, that for the house, same but with d squared. And, well, there were some further work, for instance, by Kemp Stewart in 70, I believe, 8 or so. But then came Dobrovolsky with his wonderful idea. He actually published 2 articles on the topic. He published one article in 78 in some very, very obscure journal, some obscure Polish journal. And in that article, he proved for Mahler's measure already estimate which was stronger than anything known before, something like this. And then came this glorious article in Acta Arithmetica in 99. Where he improved it further by these famous logarithms. Cube of this quotient. Cube is not really visible. It seems that, I'm sorry, I have to restart. Sometimes it dies my, or maybe now it, no. So I have to restart the program. So I'm sorry because it's too warm. So just a few minutes break. I need.
Okay.
So again, alpha, algebraic integer, not root of unity. Non-zero algebraic integer. And well, he uses 2 lemmas that will also be needed for Dimitrov's argument. Well, if P is a prime number, then we have 2 possibilities. Either Q alpha is Q of alpha P, or Q of alpha over Q of alpha P is, or maybe let me write it on the next line, or Q of alpha over Q of alpha P is a field is of degree P. So we cannot have some smaller degrees, either degree 1 or degree P between these 2 fields. And here is important that alpha is not a root of unity. Well, this is a standard exercise. Well, I'm not going to prove it. And lemma 2, if m and n are 2 integers, and they're not the same up to the sign, then alpha m and alpha n are not conjugate over Q. We cannot find in the same Galois orbits 2 powers of the same number alpha. Well, except that, well, it is plus or minus 1. So Otherwise, we cannot find. And proof of this lemma 2 is again very easy. Well, here I will sketch a proof which is easy. So let's assume the conjugate, assume that alpha m sigma is alpha n for some Galois conjugation sigma. Well, sigma must be of finite order. So for some k, sigma k must be 1. And then it is easy by just applying here sigma k instead of sigma. Then it's very easy to show that alpha mk is equal to alpha nk, m to the power k. And this implies that alpha mk minus n k is 1, and by our assumption mk minus nk is non-zero, so we obtain that alpha must be root of unity. Contradiction. Okay. And I have about quarter an hour left, and it's just enough to explain Dobrovolsky's argument. Now, let alpha be algebraic integer. So now, so alpha algebraic integer not a root of unity, non-zero. Is some prime number, and we choose P such that P does not divide the degree. So we denote f of x as x minus alpha 1, x minus alpha d minimal polynomial. And by the lemmas, we see that the numbers alpha 1 p, alpha 1, alpha d, alpha 1 p, alpha d p are all distinct. All distinct. Why they're all distinct? First of all, none of the first d can be equal to any of the second d by the second lemma, because they cannot be conjugate simply. Alpha cannot be conjugate to pth power of alpha. And and also none of these two can be equal because p does not divide d, so they must be of the same degree as d, so they must also be all distinct. So we have 2d distinct numbers. And recall that we denote by fp of x the polynomial x minus alpha 1p, x minus alpha d p. And now we consider the discriminant of these two polynomials, and by Schoenemann's congruence, or the product of these two polynomials, the discriminant is divisible by discriminant of the product FFP must be divisible by P to 2D. But this discriminant is non-zero because they're distinct. So we have a non-zero integer divisible by P to 2D. So we obtain a lower estimate for the discriminant. This is a lower estimate. A typical Diophantine argument. We have a low estimate coming from arithmetic. Now we will get an upper estimate coming from some estimates. Now, for the upper estimate, we use a representation of discriminant as a Vandermonde, or square of Vandermonde. Is the square of the Vandermonde of all these numbers. And so let us see this Vandermonde is so 1, alpha 1, etc., alpha 1 to 2D minus 1, 1, alpha D to 2D minus 1, 1, alpha D P, alpha D P 2D minus 1, and finally 1 alpha, oh sorry, alpha 1 here, not alpha D. It's here, alpha D P, etc., alpha D P 2D minus 1. And this is just a determinant, so we can estimate it using Hadamard. What does Hadamard? So we use Hadamard, we apply it to the lines. So the first D lines, it will be product of Euclidean norms of the lines. So the first D lines, the Euclidean norms are bounded for Euclidean norm of the line is bounded by what? Well, we have 2D elements, so it must be square root of 2D times maximum. Well, if the corresponding conjugate is smaller than 1, then it is just square root of 2D. If it is bigger than 1, we should take this power. So it must be maximum of 1 alpha k raised to the power 2D minus 1. And this is for first D lines. And if we norm of the line k, norm of the line D plus k, here we have pth power is the same, but we take also p in the exponent. And we see that the product of these guys is bounded by what? First D lines just give Mahler measure and raised to this power, and next D lines give Mahler measure raised to power p in this power. So we obtain, and we obtain also with this, we have this square root of 2D times, so we have 2D raised to the power D. And now Mahler measure of alpha raised to the power 2d minus 1 p plus 1. And so v squared, which is discriminant, it is just v squared, and it is bounded by square of this. So let us put it like this, 2d to the power 2d, Mahler measure. Well, I want to forget about this minus 1, so will be 4d p plus 1, and this. Very well, we have lower estimate and we have upper estimate. So we can now combine them. This is lower estimate, and this is upper estimate. Great, and this gives us the lower bound for Mahler measure. We have p divided by 2d, and this raised, this divided by p plus 1. No, should not, because it's 4d. Okay. So it will be something like 2p plus 1. Yeah. Yes. And well, now we still did not specify p, so let's take p around like 4d, for instance. By prime number theorem, we can always find p approximately equal to this order of magnitude. And so we obtain for the Mahler measure estimate like 1 over d. And this is this wonderful argument. Basically, well, lower estimate coming from Schoenemann's congruence, just divisible by huge power of p. Upper estimate coming from Adamars inequality, from the representation of discriminant, and we're done. The only unfortunate thing is this term 2d to 2d, because of which we have to take a very big p. So just to compensate, otherwise we don't
Please,
get
Yuri.
it.
Please,
Yes.
Yuri. Why
Yes.
you have to take p as big as 4d?
Well, I can take 3d.
No, can you not take it much smaller than d?
No, I obtain trivial estimate.
You just wanted p not to divide d.
Yes, but I obtain trivial. I don't obtain an interesting estimate. I need this. I need the estimate to be interesting. P should be at least bigger than 2d.
Ah, okay, okay.
Yeah.
Ah, yes, of course, of course. Yes, of course.
Mm-hmm.
Perfect.
Yeah. So this is the 78 argument. In the 79 paper, Dobrovolsky refined this argument by taking several p. He used several prime numbers. And well, if you optimize the things correctly, then you obtain this funny logarithmic bound log. Obtain this bound. Well, I don't think it makes sense for me to go further because, well, we don't formally need Dobrovolsky's argument. So very well, I think it's a good point to finish for today.